Hello, friends. Welcome to Inside Physics. I am Srinivas. Today, we are going to discuss the magnetic field due to a current carrying circular loop. Okay, so this is a topic in moving charges and magnetism plus 2 syllabus. Okay, see, prior to this class, we have discussed the Biot-Savart law and the current carrying conductor, and because of that, how much magnetic field is developed by using Biot-Savart law. In this class, using Biot-Savart law, we want to calculate the magnetic field on the axial point of the current carrying circular loop. Okay, see here, magnetic field on the axis of circular current loop. So how to calculate the magnetic field? Here we take the help of Biot-Savart law again. See what Biot-Savart law says. The magnetic field developed due to a current carrying element is directly proportional to the current element and inversely proportional to the square of the distance from the current element to the point we have taken, the position vector, the distance r. So this is the Biot-Savart law, which tells about the magnetic field because of a current carrying conductors, whether it is a straightforward current carrying element like a finite conductor. In the previous class we have derived the equation. Here we have taken a circular loop of radius r. Okay, see, from Biot-Savart law, here if you observe this diagram, the point is taken at the axial point of this circular loop. This is the center of the loop. The radius of the loop is r, and the current is flowing in the loop in this direction. So we can put the other direction also. So we, for this, see, this is the position vector. That means for calculating the magnetic field due to a current loop, we will take the small length element of this loop, and in this small length element there will be a current flowing, that is called idl, the current element. See, this length element dl bar is shown here, and because of this entire length we need to first get the small length element, and thereby by calculating the magnetic field due to this small length at this point, then we can derive the after we can derive the magnetic field due to this current carrying loop. Okay, so we will start with Biot-Savart law, and in the vector form we can write dB bar is equal to mu naught by 4 pi I dl bar cross r bar by r cube. So this is in the vector form. We can take this as, see, dl bar is the length element vector in which a small current is passing through, and r bar is the position vector. So r is the length, and between the length element and this point on the axial end, this is the point where we want to calculate the magnetic field due to this current element. Okay, so for this, what is the basis, on what basis we have written? And I have told you that dB proportional to I dl by r square. This is the basic Biot-Savart law, which says the magnetic field developed is directly proportional to the current and the length of the element, and inversely proportional to the square of the distance between the current element and the point where we have taken. Okay, so if you observe this loop, see, of radius r, the length element is actually in yz plane, right? The length element is in yz plane. This is y axis, this is z axis, and this r bar, the position vector, is in xy plane. So if you take any other length element also, here and here or here, anywhere, see, the length element, the current element is always perpendicular to the position vector. Okay, always perpendicular to the position vector. See, I will tell you once again. See, this length element is in, suppose this is a loop, you can imagine the loop like this. Okay, then this length element of the loop will be in yz plane. This is y axis, this is z axis, and this yz length element will be perpendicular to the position vector. This is in xy plane. So all the length elements, if you sum up the total length elements of small finite length, then you will get the total length of the loop. So for now we are only concentrating this on this small current element, and we will calculate the magnetic field at this point. Okay, if you observe this one, dl bar cross r bar, I have told you that this is the cross product of this length element and the radius vector, and if the magnetic field magnitude we can write as mu naught by 4 pi I dl sin theta by r square. Okay, r, one r is getting cancelled, that's why I have written r square. Here r cube is written. If this is the in vector form, the magnitude of the vector, that means the magnitude of the magnetic field, mu naught by 4 pi, is a proportionality constant. Whenever we take the proportional in this way, we need to get some proportionality constant to equate the LHS and RHS. So here I told you that sin theta between the length element and the radius vector, they are always perpendicular, so that sin theta will become 1. Sin 90 is equal to 1. So this theta, sin theta, is the angle between the current element dl, what we have taken a small element here, and the position vector. They are always perpendicular whenever you take the current length element. Okay, so this becomes mu naught by 4 pi I dl by r square. Sin theta will become 1. This is the magnitude of magnetic field. So now we come to the point here where on the axial line, if you observe, see, the magnetic field produced is always perpendicular to the plane containing the current element and the position vector. See, you should listen carefully. The magnetic field produced due to this current element is perpendicular to the plane containing the current element dl bar and the position vector. So it looks like, see, if the current element is in this vector, in this plane, and the position vector is in this plane, you can imagine a plane like this, a plane which is making an angle with axial line. So this is the plane in which both current element and the position vectors are lying. So they should be lying in the same plane. So for that plane, the magnetic field will be perpendicular. So how we can say that the magnetic field is perpendicular to this plane means, see, when you take the cross product of two vectors gives the resultant vector will be perpendicular to the plane containing the two vectors. Okay, so according to the cross product of vectors, in that way, see, if we are taking the cross product of the current element and the position vector, so to this plane the magnetic field vector is perpendicular to this plane. So now if you observe, we are divided this magnetic field vector into two components, because see, this magnetic field vector is making an angle with the axial line. See, we have taken a point here and we are measuring the magnetic field on the axial line at a point P. So when the magnetic field vector is making an angle theta with the axial line, so that we have divided the magnetic field into two components. Here the perpendicular component, see dB bar perpendicular component is directly always perpendicular to the opposite current perpendicular magnetic field element. Okay, see, if you take this here, the length element dl bar, see, because of this also there will be some magnetic field here, and if you take some current element here, because of this current element also there will be a magnetic field here, and if you take so many current elements like this on this loop, and that each magnetic field developed because of the all the current elements will be in the same way, they will be making an angle theta with the axial line, and the magnetic field vector is always perpendicular to the plane containing the current element and the position vector. So here now if you observe entire current loop and taking small current elements, this perpendicular magnetic field vector is always cancelled upon by the opposite current, this magnetic field vector. Suppose I draw another line here, this is also d bar perpendicular because of this magnetic, this current loop, current element. Okay, so in this way all the perpendicular magnetic field vectors are cancelled by the opposite component. So mutually opposite components will get cancelled, because if you take all the current elements on the entire loop, so every perpendicular element will be cancelled by the counterpart of that magnetic field perpendicular vector. So in this way the only vector component that will give the resultant magnetic field is along the x-axis, that is dB bar x. So all the perpendicular components will be cancelled, and they are cancelling each other with their opposite counterpart. So only the component which is there along the x-axis will be the resultant magnetic field developed due to this entire current loop. So in this way, if you observe, this is theta, okay, and see, I will write, I will extend this vector. So this is also theta, okay. So if this is theta and this is perpendicular to this position vector, and this will become 90 minus theta, okay, 90 minus theta. If you take this sine component of 90 minus theta, sine of 90 minus theta, that is equal to opposite side by hypotenuse, which is r by, see what r here, if you observe, or you can take with the property of the triangle, or you can take it as root of x square plus r square, this length, okay. So root of x square plus r square, this is the hypotenuse, this is a right angled triangle, so that we can write r by, r means root of x square plus r square, okay. So we have now understood the only magnetic field on the axial line is along the x-axis, and it is represented by d bar bx. Now we can write, now we can write d bar bx is equal to db cos theta. db cos theta. What is that? Along this x-axis, db cos theta. This is db sin theta. This is db cos theta. So d bar is equal to db cos theta. So db is the magnitude. Okay. So with the help of this equation, we can write here, see, r is equal to root of x square plus r square. This equation we can write as db, the magnitude, is equal to mu naught by 4 pi I dl by x square plus r square. Okay. Now see, db is equal to mu naught by 4 pi I dl by x square plus r square. Just now we have written, if you observe, dbx is equal to db cos theta. Okay. Now we have to take the only the horizontal component of the magnetic field, that is where the entire magnetic field is acting at point P due to this current loop. So this can be written as dbx is equal to, what is there, db cos theta. That means mu naught by 4 pi I dl by x square plus r square. Okay. See, what is this? Sin 90 minus theta is equal to cos theta. Cos theta is equal to r by root of x square plus r square. Okay. So in dbx is equal to here db cos theta. That means db, this is db, and cos theta is this value. Cos theta is equal to r by root of x square plus r square. Okay. See, with this equation we can write the next step as mu naught by 4 pi is always a proportionality constant. Here I dl by x square plus r square whole power 3 by 2. Okay. 1 plus 1 by 2, I have written x square plus r square whole power 3 by 2. Okay. See, and there is an r here. Okay. See, if you observe this magnetic field, this magnetic field is only because of this current element only. So we want the magnetic field due to entire current loop. So what we have to do is the length element, current length element, is taken for the entire current loop. What is the length of this current loop which is having a radius r? Means the total length is the perimeter of this circular loop. What is that? L, we can say L, that is 2 pi r. This is the length of the total length of the current loop, which is nothing but perimeter. This is the perimeter. Now if you see this equation, now if you, in the place of dl, we need to put L is equal to 2 pi r, because this is the magnetic field due to this small current element only. Now we want the magnetic field due to entire circular loop. So for that we need to put L, total length 2 pi r, in place of dl. So the equation becomes, now B is equal to, this is B is total magnetic field, mu naught by 4 pi I dl. Okay. See, I dl r, sorry, we need to put in place of L dl, we need to put 2 pi r into r by x square plus r square whole power 3 by 2. Okay, see, this is the total magnetic field due to the entire current loop. So further moving, this is equal to mu naught by 4 pi. See, I mu naught by 4 pi I 2 pi r square by x square plus r square whole power 3 by 2. So this is the magnitude of total field. If you want in vector form, if you can take the vector form of this, we can write b bar is equal to mu naught by 4 pi. See, here we can cancel pi and 2 in terms of 2 times. We can write mu naught by 2 pi gets cancelled. So here I nothing but I r square by x square by r square whole power 3 by 2 into I cap, a unit vector along x direction. So this unit vector I cap will represent the direction of this entire magnetic field. If you observe, pi gets cancelled, 4 gets is 2 times, and I 2 I r square by this one. Okay, so now this is the magnetic field, total magnetic field in the vector form because of this current carrying loop. Okay, so here if you observe, if you want to take the current carrying loop and if you want to calculate the magnetic field at its center, if you observe at its center the x will become 0. The distance between the point is taken at the center and the x part will become 0. So in that case, at the center of the loop, at the center of loop, this equation becomes b bar is equal to, see, mu naught by 2 I r square by, see, x will become 0 and r to the power of 3 into I cap. This becomes, see, not pi, sorry, this is I, this is mu naught. So mu naught I into r by this one is, okay, mu naught and r will gets cancelled, this becomes 2r into I cap. So this is the magnetic field at the center of the loop, mu naught I by 2r. So in this way we can derive the magnetic field due to a current carrying loop using Biot-Savart law. Okay, so what will be the magnetic field direction because of this loop? How it will look like when you represent with some diagram? We will see that. See, this magnetic field, and we draw the magnetic lines of force around the loop. Okay, so if this is the loop which we have taken to calculate the magnetic field, and the magnetic lines of force will be going like this. Okay, will be going like this. See, if you can take the magnetic field direction, if you want to get the magnetic field direction and the current is in this direction, see, if you can put the fingers, see, the fingers of right hand in the current direction, see, in this direction, see, my fingers, four fingers are in the direction of the current in the loop, then the thumb gives the magnetic field direction in this way. And here also, see, the loop, the magnetic lines of force are coming here, and again here also we can take a loop like this, so they will be moving in this direction. Okay, and here, okay, see, here the current direction will be in the into the board at this particular point, so that the magnetic lines of force are in this way. Okay, so here is the representation how the magnetic field lines are there around the current carrying loop. So this is about the magnetic field developed around the current carrying loop. Okay, so in the next class we will see some more topics in moving charges and magnetism. Okay, thank you.